Hello everybody, this is Dr. Webb and welcome to this abstract algebra video where we are going to be talking about a way of combining groups together, which is called an external direct product. So what exactly is an external direct product? Well, let's take some finite number of groups, G1, G2 through Gn. These groups can be anything. And then we can take what's called the external direct product of the groups, written as G1 with sort of a circle plus, G2 circle plus up to Gn. And what this is it is n tuples. So we started off with n groups. It is n tuples where in the ith component, in the ith slot, is some element of Gi. Right? And so the direct product is all of these possible n tuples, where the ith component is an element from Gi. So this does form a group where the group operation is done component by component. In other words, if we have sort of G1 up to Gn, and we want to combine this with H1 up to Hn, then this is all going to be done component by component. So G1 and H1 are both in big G1, so we can talk about G1 H1, G2 H2, etc., etc., Gn Hn, where this combining of G1 and H1 in the first slot, this is done according to G1's group operation. The combination of G2 and H2 in the second slot, that's done according to G2's group operation, all the way down to the combination of Gn, Hn in the last slot, that is done according to Gn's operation. And so this does form a group. In this group, the identity element is the element where the identity for each respective group is in the right component. So it's E1, E2 up to En. And so that's the identity. So when you apply it to any other element component-wise, it doesn't do anything to each one. There is no cross combination between components. Everything is kept broken apart component by component. And lastly, if we want to take the inverse of some element of the direct product, then we just take the inverse component by component, where again, this inverse, this is according to whatever the group operation is for that respective group. So if G1, if its group operation is addition, that means inverse would really, instead of being G1 to the minus 1, it would really be minus G1. If it's multiplication, then it would be, sort of the reciprocal. But it also, you could have permutations in one of these slots, and in that case, the inverse would be sort of the inverse permutation. So let's look at a quick example of this. So a group that we've talked about an awful lot is the Klein-4 group. And so let's recall, we thought about the Klein-4 group a number of different ways. Let's write it right now as E, A, B, A, B, where A, B, and A, B, these are all order 2. And so if you remember, we proved that this is the only non-cyclic group of order 4. And this happens to be isomorphic to Z mod 2Z plus Z mod 2Z. And Z mod 2Z plus Z mod 2Z, this also has 4 elements, which should make sense since they're isomorphic to each other. So Z mod 2Z plus Z mod 2Z. Its identity element, so since the operation of both of these is addition, its identity element is 0, 0. And then there's 1, 0, 0, 1. And then adding them together, we have 1, 1. where the group operation here is addition component by component mod 2. And so, the quick isomorphism between these from V4 to Z mod 2Z plus Z mod 2Z is going to be phi of the identity goes to 0, 0. We can have phi of A go to 1, 0. Phi of B go to 0, 1. And then phi of AB, so this is going to equal phi, well, remember, our operation in Z mod 2Z plus Z mod 2Z is addition component by component. And so this is really going to be phi of A plus phi of B when we change to the other operation. And so that's going to be 1, 0 plus 0, 1, which gives us the element 1, 1, the last element in our group. Okay, and this phi is, as we can see by construction, it is a bijection, and by construction we also made it obey the group law, and all the elements except for the identity are group 2, are order 2, and so this all works out very nicely. Okay, so suppose that that you have some element of the external direct product, and where each of the components have finite order in their respective groups, then how do you calculate the order of that element in the direct product? And it's going to be equal to the lowest common multiple of the orders of each of the components. And so let's give a quick proof of this. So first thing to note is that let's call this least common multiple K. And so the first thing to note is that since G to the I divides K for all I, then this means that G to the I to the K is going to be the identity for whatever, for big GI. And so our element raised to the kth power, well, this is just doing it to the kth power component by component, which is going to give us all identities, and this is the identity in the direct product. And so this tells us that the order of G1, comma Gn, the order of this element in the direct product has to, I have one too many lines there, has to divide K. On the other hand, since, let's let the order of the element in the direct product, let's call this T, and so this means that G to the I to the T is equal to the identity for the group big GI, and so this implies that the order of G sub I divides T for all I. And so since the order of G sub I divides the order of the big of the element in the direct product for every component, that means that it has to be a multiple of all of these orders. And so this means that by the definition of the LCM, since it is a multiple of all these orders, the LCM of these orders, which is K, has to be less than or equal to T. And so on the one hand, we have that the order divides the LCM. On the other hand, we have that the LCM is less than or equal to the order. And so putting these two together, we get that they are the same. So putting together that the order of the element in the direct product divides the LCM, and that the LCM is less than or equal to the order. The only possibility for both those things to be true is if the two are equal. Okay, so we had that as a lemma. So what's that a lemma for? Well, it's for this basic theorem, which is that if G and H are both finite cyclic groups, if G and H are both finite cyclic groups, then their external direct product is going to be cyclic if and only if the order of the GCD of the order of the two groups is equal to 1. Right? So the two orders have to be coprime for them to be cyclic, and if they are coprime, then it is cyclic. Okay, so this, using the fact that we know how to take orders, is going to make this pretty simple. So on the first hand, let's do it backwards first. So let's suppose that the GCD of G and H is equal to 1. If the GCD of G and H is equal to 1, then this means that the LCM of G and H is equal to the product G times H. In fact, this is an if and only a statement. And so then, if I let G be generated by little g, H be generated by little h, then the order of G is equal to the order of big G. The order of little h is equal to the order of big H. And so then the order of G comma H by our lemma is equal to the LCM. But since these two are relatively prime, the LCM is equal to the product. And the product of G and H, well, if you think about how many things are there total in G plus H, well, so this is all tuples of A comma B, where A is in G, B is in H. And so this means that we have the order of G possible things to put into the first slot, and the order of H possible things to put into the second slot. So how many things total are there? Also G mod H. And so the element G comma H has order, the same order as the order of the group. And so then that means that G plus H is generated by this element. Okay, so that proves the first direction. Actually, proving the back direction first. So now we need to prove the forward direction. So to prove the forward direction, we're actually going to do this by contrapositive. So let's suppose if the GCD of G and H is not equal to 1, that must mean that it's bigger than 1. So let's suppose that the GCD of G and H is greater than or equal to 1. Then this means that the LCM, if G and H have divisors in common, then the lowest common multiple of the order of G and the order of H is going to then have to be less than the order of G times the order of H. It's actually equal to, this is a fun fact from number theory, is that the LCM of two numbers is equal to their product divided by their greatest common divisor. And so if the greatest common divisor is bigger than 1, in fact we need it to be not greater than or equal to, we need it to be absolutely bigger than 1. Why aren't you erasing? That's better. And so if the GCD is bigger than 1, then our denominator is bigger than 1, so we end up with something less than the product of G and H. And then if we note that for any G sub 1, H sub 1 in the direct product, well, G sub 1, H 1 raised to this LCM well, this is going to be equal to raising each component to the LCM. I'm just going to write LCM for short. And so since the LCM is a multiple of G and H, then that means that it is a multiple of the order of the group. And so then by from what we saw in the last couple of videos about Lagrange's theorem, the order of G1 divides the order of G, and the order of H1 divides the order of H. So since the order of G1 divides G, and the order of H1 divides H, this means that G1 to the LCM, H1 to the LCM is equal to the identity. Let's call it E sub G, E sub H. And this works for any element G sub 1, H sub 1 inside of there. So none of the elements have a high enough order to generate the entire group. So G1, H1 cannot be a generator. And so since no elements can be generators, this means G plus H is not cyclic. Okay. So to finish this off, as a quick application of this theorem to groups Z mod NZ, well, Z mod NZ, these groups are, Z mod NZ is a cyclic group of order n, generated by 1. And so if we have the direct product of two of these groups, so if we have Z mod NZ plus Z mod MZ, then this is going to be isomorphic. This is going to be cyclic by the theorem above, if and only if the GCD of n and m are equal to 1. And if they are cyclic, then they're going to be isomorphic to Z mod n MZ. Because Z mod n MZ, this is a cyclic group. So this is cyclic of order NM. Z mod NZ plus Z mod MZ, the size of this is also going to equal NM. And so these two have the same number of elements, but since Z mod NMZ is cyclic, they're only going to be isomorphic if the GCD of these two elements of N and M is equal to 1. And this is exactly what the theorem above says. So that is all for this video. I will see you again soon.